Solving compound inequalities. Now we're going to break this up into two pieces. We can do a compound inequality with an and. We can do a compound inequality with an or. So we're going to start with an and. What are we talking about when we talk about compound inequality? Just like a compound sentence in English, we're taking two inequalities and working with them at the same time. When considered together, two inequalities form a compound inequality. A compound inequality containing and is only true if both inequalities are true. Its graph is where the graph of the two inequalities overlap. This is called the intersection of the two graphs. So we're going to take a look at each of the inequalities as part of our compound inequality separately. We're going to look at their solutions separately, and then with an and compound inequality, where they overlap, where they intersect, will be the solution set for the total compound inequality. Now when I'm thinking of compound inequalities, I kind of think of a Venn diagram. We do Venn diagrams in social studies, in English, and we're talking about two sets of items, and what about them is independent of each other, and what about them kind of overlaps. So I tend to think of some sets. So I imagine that if I have a set of all the students who would be on the silver team, and I have a set of all the students that are in band. So there are students that are on the silver team that are not part of the group in band, and there are definitely students that are in band, including 6th graders, 7th graders, green, white, and bronze team, who are in band that are not considered part of silver team. So if we made an announcement and said we would like to have all the students who are in silver team and also in band, please report to the auditorium. We would have a small set of people. There would be people on the silver team who would not be going. There would be people in the band who would not be going. There would be a small intersection of those two sets that would be part of this compound inequality. If we think about it, like if we're talking about giving directions to someone and we say, meet me at the intersection of East Street and Main Street, we know exactly where you're talking about. We're talking about those two come together and overlap each other. It's a small set. If we think about East Street, that's a long distance. If we talk about Main Street, that's a long distance. Where they overlap and is a small set. So we're really talking about, when we say and in this particular case, we're talking about kind of really bringing it down to a smaller piece of the two, where they intersect each other. So let's look at this as far as an algebraic inequality. 7 is less than a plus 2, which is less than or equal to 11. So we can write these and compound inequalities kind of as one flowing inequality. What's in the middle here is really part of two different things. I really have 7 is less than a plus 2, so I've kind of chopped it off where my other inequality is. I also have that a plus 2 is less than or equal to 11, so I've chopped it off at the first inequality. So the first thing I really want to do is split this up into its two parts. I have that 7 is less than a plus 2. I also have that a plus 2 is less than or equal to 11. Now notice when this is written, my inequality symbols are facing the same direction. That's rather important. We don't want to have them going opposite directions. That kind of creates for weirdness. We want to say is less than, is in less than. So I'm starting with the smallest piece here. This is in the middle, and then this is the largest over on the end. I'm going to solve each of these inequalities independent of each other first. So I'm going to look at solving this inequality, end up with 5 is less than a. I'm going to solve my second inequality, which ends up with a is less than or equal to 11. So I've got 5 is less than a, and at the same time, a is less than or equal to 11. To graph this, the graphing is really going to help you figure out what this final inequality solution set looks like. So I'm going to graph these two inequalities separately from each other. So my a is greater than 5, which is just this one switched around. A is greater than 5. I've got an open circle on the 5, and my solution set is going to the right. A is less than or equal to 11. I have 11 as my boundary, solid circle, my solution set going to the right. So I'm looking to see where these two overlap, where they intersect. And where they intersect is here at 5. Now 5 is only included in one of these sets. 5 is not included in this first set, although it is in the second. Since I'm looking for where they overlap, they do not overlap at 5. So I'm not including the 5, but that's a boundary for me. I'm including what's in the middle, because that overlaps. And then they both include 11. So 11 is going to get a solid circle because that's part of both sets. So I'm really kind of splitting this number line up into 3 parts here. I have what's less than 5, I have what's between 5 and 11, and I have what's greater than 5. And it's easy, again, to go back and check to see if your solution set makes sense. I could pick a number that's less than 5. How about 0? I could plug 0 in here. If I plug 0 in here, I get 2. 7 is less than 2, which is less than 11. That doesn't make any sense. So it makes perfect sense that this side of the number line is not part of my solution set. Let's try 7. 7 plus 2 is 9. 7 is less than 9, which is less than or equal to 11. Yep, that makes sense. So this works, that this is my solution set here. If I pick a number that's larger, let's say 20, 20 plus 2 is 22. 7 is less than 22, yes. And that's less than or equal to 11, no. So this section of the number line is not a solution either. So my intersection looks good. Let's boil it down to one inequality that's our solution. And again, we're writing things in set notation here. So I have A such that 5 is less than A, which is less than or equal to 11. And I can really pull this inequality straight from my number line. I'm going to start with 5. That's the least number, so I'm going to say it's less than. There's my variable in the middle, which is A. And my 11 is going to go at the other end, and that's a less than or equal to. So I can really pull this kind of three-part inequality, this compound inequality, right from my number line. All right, let's take a look at a couple of others. Solve negative 4b plus 13 is greater than or equal to 29, and 10 is less than 6b minus 14. So we can write them here as this and piece, especially when we don't have something in common in the middle. And then we're going to graph this. So we're going to solve each of these independent of each other. I have b is less than or equal to negative 4, and 4 is less than b. I'm going to take a look at each of these graphs, the solution sets on the graph, for them one at a time. B is less than or equal to negative 4, solid circle on the negative 4, line going to the left, my solution is less than. B is greater than 4, I've got an open circle on the 4, and my line is going to right. Again, this is an and, so I want to see where they intersect. Now as I look at these two number lines, they don't overlap anywhere. So there is no intersection, the sets don't overlap, which means there's no solution. So there is no one group of numbers, or even one number, that will make both of these true at the same time. That's what this solution is telling me. There's nothing that I can do to make them both happen at the same time. So you may end up with that there's no solution to your answer. You want to take a look at what you have specifically before you decide what your solution will be. Again, I don't want to just end up with this, because there's more meaning. This makes it look like there are numbers that will make it work when there actually are. So we want to boil it down to what we really mean by that, by this solution. Word problem. A company is manufacturing an action figure that must be at least 11.2 centimeters tall and at most 11.4 centimeters tall. Write in graph a compound inequality that describes how tall the action figure can be. So I'm going to use my variable h for the height of this figure, and I know that at least it has to be 11.2, so that's the smallest it's going to be. I'm going to set it equal to because it can be at least 11.2. It can include that. My h. And then at most it's 11.4. That's the highest it can be, and it can include the 11.4 at most. So I'm including the 11.4. So here's my compound inequality. They wanted us to graph it also. So I have 11.2 and 11.4 on my number line here, as those are my boundaries. Again, with a compound inequality, I might have two boundaries. I've got two boundaries going on there. They're both included, so I've got solid circles and then my line in the middle. So when we think about an and, we want where they overlap. Where they overlap can look different depending on what type of inequalities we're starting with, but we want to think about what the two graphs look like independent of each other, and then our final solution is going to be where they overlap, that intersection, that and it's going to be a smaller set than what we started with.